Hello my friends and welcome back to the You Can Do TV channel. We're at Havel's Alwar plant. The manufacturing process of wires begins with the procurement of high-quality 8 mm copper rods, which are the basic raw material for wire production. These copper rods are drawn to the required size in a controlled process that includes online annealing. Annealing is a critical step where the copper is heated and then cooled slowly. This process increases the ductility of the copper while reducing its hardness, making the material more flexible and easier to work with. This insulation allows the wires to operate with a conductor temperature of up to 105 degrees Celsius during continuous operation, ensuring safety and reliability. After insulation, all cores are passed through high-voltage spark testers. These testers detect any contamination, imperfections, or pinholes in the insulation layer, ensuring that the wires are free of defects. The insulated wires are then coiled in an automatic coiler to guarantee that the delivery length is 100% accurate. Safety is a priority throughout the process, and numerous tests are conducted before the wires are packed and dispatched to ensure that they meet the highest standards. Beyond wire manufacturing, the company also produces low-tension (LT) and high-tension (HT) power and control cables. HT power cables are manufactured up to 66 kV, while LT power cables and copper control cables are produced up to 1.1 kV. The production of these cables follows a well-structured process. After procuring raw materials like copper or aluminum rods, the wires are drawn to the required size. Following this, the annealing process is repeated for HT screened cables. Once annealed, the next step is stranding, where the conductor is formed according to the required design specifications. For HT screened cables, the conductors are then insulated with either PVC or cross-linked polyethylene, XLPE, depending on the application. To ensure the best performance, a triple extrusion process is employed for insulation. This process ensures perfect bonding between the insulation and the semiconducting layers, which prevents the formation of air voids that could lead to premature cable failure. The screened cables are then subjected to insulation screening with metallic shielding. A copper tape is applied helically over the insulated and screened cores, providing 100% coverage and enhancing the cable's durability. Once the cores are insulated and screened, they undergo laying up, where they are arranged according to the required design. The cable is then protected with inner sheathing, armoring, and outer sheathing, depending on its intended use. Finally, the cables are rewound onto wooden drums, tested rigorously to meet the required specifications, and then packed for dispatch. This comprehensive process ensures that only high-quality, reliable cables reach the customers, providing them with secure and worry-free electricity connections. Interconnections between countries. Submarine power cables also play a vital role in creating interconnections between countries' electrical grids. These interconnections provide energy security by allowing electricity to be imported or exported based on demand and supply. For instance, NordLink, a 623-kilometer HVDC submarine cable linking Germany and Norway, transmits up to 1.4 gigawatts of power, equivalent to the needs of approximately 3.6 million households. The cable helps balance Norway's hydropower surplus with Germany's renewable energy needs, contributing to a more resilient and interconnected European power grid. Similarly, the Elec Link submarine cable between the UK and France is an interconnector that strengthens energy exchange across the English Channel. It is capable of carrying 1 gigawatt of electricity over its 51-kilometer length. The Dondrea U-tronic boring and facing heads are advanced tools designed for medium and large-scale operations on boring machines, machining centers, and specialized machines. These NC, numerical control, heads enable precision machining for a variety of applications, including boring, facing, threading, and machining complex radii. General features. U-tronic heads connect to the U-axis of CNC machines, allowing for synchronized interpolation with other machine axes. This capability facilitates operations such as external and internal facing, cylindrical and conical boring, back-facing, and machining concave or convex surfaces. The heads are available in 6 standard models, ranging in diameter from 360 mm to 1000 mm, and can accommodate tools with either manual or automatic tool change systems. Additionally, custom models with diameters up to 1600 mm are available, featuring integrated reduction gears, counterweights for self-balancing, and special configurations like dual slides. The heads are designed for versatility, compatible with both manual and automated systems, and are adaptable for use with pallet systems. They feature internal coolant pathways to ensure optimal cooling during operations, with a maximum coolant pressure of 40 bar. Command and control. The direct integration with the U-axis of CNC systems allows the U-tronic heads to execute a wide range of operations, from basic boring to complex radius and spherical machining. This integration ensures precision and adaptability for intricate machining tasks. Key prearrangements. Internal pressurization. To protect sensitive components such as servo motors and transducers, the head includes an 8.5 mm internal pressurization channel. An air inlet at 0.5 to 1 bar prevents the ingress of liquids and dust. Automatic greasing. A dedicated channel enables automated greasing, ensuring consistent lubrication and reducing manual maintenance requirements. Coolant supply. Internal channels deliver coolant directly to the tool through threaded holes near the slide, maintaining cutting efficiency and tool longevity. Balancing and applications. For optimal performance, counterweights can be added to balance tools that are offset from the head's axis. Threaded holes on the rotating body make this adjustment straightforward. Interface flanges are available in various configurations: manual, automatic, extended, or angular, to suit different machine setups. The U-tronic heads can also integrate automatic tool changing mechanisms, making them ideal for fully automated machining environments. Coil handling and preparation. The process begins with the coil lifting car and coil rack, which securely transfers the steel coils to the uncoiler, single drum with center adjusting, for steady unwinding. A hold-down roll and coil peeler facilitates initial strip threading, preparing it for the next stages. The pinch leveler ensures the strip is flattened and guided effectively, minimizing defects. The shear and end welder machine trims and welds strip ends to maintain continuous production without interruptions. Accumulation and forming. The spiral strip accumulator, horizontal type, temporarily stores the strip to ensure consistent feeding during coil changes. The forming part, gear coupler type, shapes the strip into a cylindrical form by gradually bending the edges, preparing it for welding. Welding and cooling. High-frequency welding joins the edges seamlessly, creating a robust longitudinal weld. The welded tube passes through the cooling bath to dissipate heat, maintaining structural integrity. An online ECT, eddy current testing, system inspects the weld quality, ensuring the tube meets stringent standards. Sizing and cutting. The tube proceeds to the sizing part, gear coupler type, where its dimensions are precisely adjusted to meet specifications. The milling cutoff machine, orbital tube blade type, then cuts the tubes to the desired lengths with high accuracy. Finishing and packing. Post-cutting. The end-facing and chamfering machine smoothens the tube ends for safe handling and assembly. The air blowing system removes debris or residue. The tubes are packaged semi-automatically using the semi-auto packing system, and the manual strapping machine ensures secure bundling for transport. This advanced production line integrates automation and precision engineering to deliver consistent, high-quality tubes for various industrial applications. The Gleason 150 SPH spheric gear honing machine represents a leap forward in gear finishing technology, employing the patented spheric honing process to enhance precision and efficiency. Designed for high-volume production, the machine is tailored to finish hardened spur and helical gears up to 150 mm in diameter, achieving results in half the time of traditional methods. The process begins with the automatic loading of the workpiece via a conveyor in a standard automation cell. The gear is clamped securely before undergoing stock dividing and roll checks. The innovative spheric honing then fine-tunes tooth geometry, reduces errors, and optimizes flank contact, producing quieter gears with superior performance. After honing, the workpiece is rechecked and rejected if it fails quality standards. Tool changeovers, such as honing ring replacements, are streamlined for minimal downtime. Dressing of the honing profile and inner diameter is performed using a patented process, quadrupling tool life and reducing costs. The machine is powered by Siemens 840 DCNC and Gleason Windows-based software, enabling intuitive setup and automated flank form corrections. High-speed direct drive honing doubles processing speed, while integrated automation cuts changeover time by 70%. The production of ERW, Electric resistance welded tubes and pipes plays a vital role in the oil and gas industry, providing high-quality piping solutions for applications like transmission lines and casing. ERW pipes are manufactured by cold-forming steel into cylindrical shapes and welding the longitudinal seam using high-frequency induction, HFI, welding. This method ensures precision, strength, and cost-effectiveness. ERW pipes for oil and gas applications are typically produced with diameters ranging from 21.3 mm, 1/2 inch, to 609.6 mm, 24 inches, and wall thicknesses of 1.5 mm to 20 mm. These pipes can be manufactured in lengths of up to 12 meters for standard requirements, though custom lengths are available. Production lines for ERW tubes include processes such as uncoiling, leveling, edge preparation, forming, welding, seam planishing, sizing, cutting, and non-destructive testing, NDT. Advanced NDT methods like ultrasonic and radiographic testing ensure compliance with standards like API 5L, ASTM A53, and A252, ensuring durability and safety in critical oil and gas operations. Modern ERW pipe manufacturing plants are designed for efficiency and scalability, with annual capacities ranging from 100,000 to 1 million tons. Automated production systems enable mill speeds of up to 120 meters per minute, significantly reducing production time while maintaining strict quality controls. This capacity and precision ensure a reliable supply of pipes for the global oil and gas industry. The electric resistance welded, ERW, profile production industry is a significant sector in metal manufacturing, focusing on the production of welded tubes, profiles, and structural shapes. ERW technology is used to create welded pipes and profiles from steel, with applications in various industries such as construction, automotive, aerospace, and energy. In ERW profile production, the process involves passing a coil of steel through rollers that shape the material into a profile. The edges of the profile are then heated using electric resistance and welded together, forming a seamless product. This process can produce profiles with diameters ranging from 10 mm to over 1,000 mm, with wall thicknesses typically ranging from 0.5 mm to 30 mm. The global ERW pipe production capacity is estimated to be around 70 million tons annually, with the market seeing a steady growth rate of 3 to 5% per year. Key producers of ERW profiles are located in regions with strong industrial bases, including China, India, and the United States. ERW technology is valued for its cost-effectiveness, energy efficiency, and ability to produce high-quality, precision profiles. Advancements in welding technology and automation continue to improve production efficiency and product quality, driving the growth of this sector in the global market.
There's something mesmerizing about the iron casting process at a large steel foundry. The journey begins with molten iron. Its orange glow lighting up the entire workshop as it's transferred in massive ladles from the furnace. Every step requires focus and teamwork. The crew moves with precision, guiding the heavy ladle overhead along rail tracks to the casting area. Here, the molds have already been set up and preheated, ready to receive the hot metal. With careful coordination, the ladle is tilted and streams of molten iron flow into the molds, filling every cavity. The sound and heat are intense, and watching the liquid metal take shape is unforgettable. After pouring, the molds are left to cool as the iron begins its transformation into solid form. The skill involved in handling such high temperatures and heavy equipment is remarkable. Every detail, from monitoring the temperature to ensuring the molds are properly aligned, affects the final casting. This process is more than just industrial. It's a display of experience, discipline, and technical mastery. Seeing it all come together is genuinely inspiring for anyone fascinated by how things are made. Automation takes center stage as the steelastic apexing machine precisely applies a rubber apex to tire beads. Rubber is extruded, shaped, and pressed onto each bead with perfect consistency, all at high speed. Each ring travels down the conveyor, guided by rollers and trimmed for flawless edges. In the next stage, a robotic arm places a blue ring on top of another for perfect alignment, before lifting the set away for inspection and packing. It's fascinating to see this level of accuracy and speed in tire production. Manufacturing toruspherical heads and tank ends is a precise and powerful process. It all starts with flat steel sheets, which are carefully measured and cut to size. These sheets are positioned under massive hydraulic presses, where intense pressure forms the curved, toruspherical profile. The edges are shaped for a perfect fit. Technicians monitor each stage closely to ensure flawless curves and consistent thickness. For stainless steel, extra care is taken to avoid surface defects and maintain strength. Watching the transformation from flat metal to robust curved heads is truly impressive. Every step highlights the technical expertise required to produce components that will safely serve the transport and storage industries. Spot welding robots are the backbone of automotive body assembly. The process begins as steel panels are precisely positioned by automated systems. Robotic arms equipped with welding guns move in, pressing electrodes on key points, and delivering powerful bursts of current to fuse the metal. Sparks fly as dozens of welds are completed in seconds. The speed and consistency are stunning. Every weld is exactly where it needs to be. Watching this level of automation in action really highlights the future of car manufacturing. This ship propeller is absolutely massive, 110 tons, and over 10 meters across, built for a giant container vessel. Moving something this heavy pushes cranes and logistics to the limit, yet the team pulls it off perfectly. The transformation of raw steel into building materials happens in seconds on this production line. Production begins as cold steel sheets are shaped by powerful rollers, forming precise profiles. Next, mechanical cutters slice the steel to exact lengths. Every step is fast and controlled, delivering finished products ready for use across the construction industry. A crankshaft is mounted on precision grinders, where automated wheels remove microns at a time for a flawless finish. Coolant flows to prevent overheating, while digital controls ensure exact tolerances. Watching the metal turn mirror smooth under the grinding wheel is seriously impressive. This is the kind of detail that keeps engines running strong. It's amazing to witness how a massive railway crane is built step by step. Fabrication begins with welding and machining the huge steel frame, followed by precision boring for key joints. Skilled technicians assemble mechanical, electrical, and hydraulic systems, routing countless cables and installing complex piping. Each section is lifted and mounted with absolute care. Once the structure is complete, technicians integrate the control cabinets and connect all sensors. The massive boom is then assembled, with final checks before operation. Watching all these parts come together into a multitasker is truly impressive. Few sites match the power of a 3-roll plate rolling machine bending thick steel for a pressure vessel. Here, a 130 mm ASME certified plate is fed between giant rolls, which apply massive force to create a perfect curve. Precision controls keep every bend accurate. Watching such heavy material shaped with this level of control is truly impressive. Industrial engineering at its best. Watching the zany Servo Master 3200T in action is truly impressive. The process starts with heavy steel components fabricated and machined to precise tolerances. Engineers handle complex boring and milling, then assemble the massive press frame. Servo motors and advanced lever systems are integrated, delivering both speed and power. The press is equipped for quick mold changes and exact stamping, handling demanding production cycles with ease. Seeing such large-scale machinery operate with this level of control and accuracy is thrilling for any manufacturing enthusiast. Every stage reflects the dedication and expertise behind its creation.
Fuel (LNG) tank panel milling. The manufacturing process begins with large aluminum sheets being loaded into double gantry skin milling machines. These machines precisely mill the aluminum into orthogrid patterns designed to form the lightweight but strong panels for the Vulcan Centaur's propellant tanks. Once milled, the aluminum panels are transferred to a brake form and bump pressed to achieve the precise curved radius necessary for fuel tank barrel sections. These barrel sections form the body of the liquid natural gas (LNG) fuel tank. Additionally, rings and other structural components are precision milled to ensure they fit precisely with the other tank parts, contributing to the overall structural stability of the booster. The aft thrust structure, a critical component for withstanding the immense forces experienced during launch, is milled and then moved to an assembly jig. Here, it is mated to the truss structure, which supports the entire booster. While the LNG tank is being constructed, the oxidizer, liquid oxygen or LOX tank is simultaneously built using similar techniques. The oxidizer tank panels are formed, and the intermediate bulkhead, which separates the LOX and LNG tanks, is installed. These components are transferred to the tacking tower, where the initial assembly takes place before welding. Next comes the welding phase, where circumferential friction stir welding is employed to join the various panels and domes of the tanks. Friction stir welding uses frictional heat generated by a rotating pin tool to stir and forge the parent metal materials together, resulting in a high-strength, lightweight joint without the need for filler materials. This process is used to build both the LNG and LOX tanks. For the LNG tank, the aft dome is mated to the cylindrical fuel tank barrel, and the oxidizer feed line is added. The fuel tank and oxidizer tank are then welded together to create the booster's main stage. The Vulcan Centaur qualification hardware built at United Launch Alliance's ULA factory in Decatur, Alabama, represents a significant leap forward in space launch technology. This state-of-the-art process integrates various manufacturing techniques to ensure the rocket's components are built with precision, durability, and performance in mind. The factory, which spans 1.6 million square feet, is where ULA produces rockets like the Atlas V, Delta IV Heavy, and Vulcan Centaur. ULA has a long-standing reputation for reliable launches, successfully deploying missions to every planet in the solar system and supporting national security, science, weather, and communication satellites. While the launch happens in Florida or California, the rocket's journey to space begins in Decatur. The Vulcan Centaur is designed to improve ULA's rocket lineup with advanced manufacturing techniques, optimized for strength, weight reduction, and fuel efficiency. Here is an in-depth look at the step-by-step process involved in building key components of the Vulcan Centaur, particularly its fuel, LNG, and oxidizer, LOX, tanks, structural elements, and final assembly. Once the tanks are fully assembled and welded, they undergo rigorous pressure testing to verify the strength and integrity of the welds. Pressure testing ensures that the tanks can withstand the stresses of fuel loading and the extreme forces of launch. After passing the pressure test, the tanks are moved to the spray-on-foam insulation (SOFI) booth. In this phase, a protective foam layer is applied to insulate the tanks from the intense acoustics and vibrations generated during launch. This foam also provides thermal protection for the cryogenic fuels housed inside. With the tanks insulated, the next step is final assembly. In this stage, crucial components like engines, wiring, and avionics are added to the booster. The integration of these systems is meticulously carried out to ensure the rocket functions as a cohesive unit. The oxidizer tank skirt and thrust structure are prepped for mating, and the completed booster is transferred to the final assembly area, where all major structural components are joined. Booster to structural test and pressure test facility. Before the Vulcan Centaur booster is cleared for flight, a structural test article is built and subjected to a variety of tests. This includes pressure testing, which ensures the fuel and oxidizer tanks can handle the stresses of being fully loaded with cryogenic propellants and subjected to launch conditions. Additionally, Structural tests ensure that the booster can handle the dynamic forces experienced during liftoff and flight. Once testing is complete, the Vulcan Centaur booster is prepared for transport. The final stage of preparation happens at the assembly facility where the rocket is readied for shipment to ULA's launch sites, either Cape Canaveral Space Force Station in Florida or Vandenberg Space Force Base in California. The rockets are loaded onto ULA's RS rocket ship, a specially designed cargo vessel, and make the journey to the launch site. The Vulcan Centaur's first launch is set to open a new chapter in space exploration. Orion, NASA's next-generation spacecraft, is designed to take humans further into space than ever before, with its first flight test marking a major milestone. The process of preparing the Orion crew module for this test began several years ago. The crew module arrived at Kennedy Space Center in Florida and was transported to the Neil Armstrong Operations and Checkout Building for manufacturing, processing, and pre-flight testing. Over the next 2 years, Lockheed Martin, NASA engineers, and technicians built the module from a green shell into a fully functional spacecraft. The Orion crew module underwent numerous tests, ensuring its readiness for the flight test. In addition to the crew module, Orion's service module also arrived at Kennedy Space Center for build-up and processing, where it was equipped with protective fairings for the early stages of launch ascent. The installation of Orion's heat shield was a critical step, designed to protect the spacecraft during re-entry into Earth's atmosphere, where it will face intense heat as it splashes down into the Pacific Ocean. The importance of Orion's heat shield cannot be overstated. As Molly White, a heat shield engineer for Orion, explains, the spacecraft will face extreme temperatures due to friction with Earth's atmosphere during re-entry. The heat shield, measuring 16.5 feet in diameter and weighing about 1,000 pounds, is designed to withstand surface temperatures of around 4,000 degrees Fahrenheit during the first flight test. It incorporates innovative materials that can tolerate even higher temperatures, up to 6,000 degrees Fahrenheit. The Orion crew module was stacked atop the service module, and tile panels were installed around the spacecraft. The final system tests followed, ensuring all systems were operational before flight. By September, the Orion stack was moved to the Payload Hazardous Servicing Facility, where it was fueled ahead of its flight test. Orion's launch abort system, designed to protect astronauts during launch by pulling the spacecraft away from the rocket in case of an emergency, was integrated in late September. This system ensures the crew's safety during critical moments of the mission. In parallel, preparations for the Delta IV Heavy rocket, which will launch Orion, were underway. The rocket components arrived at Cape Canaveral, the launch vehicle was positioned on the launch pad. Orion was integrated with the rocket, and final tests confirmed readiness for launch. As Orion prepares for its first test flight, it marks a crucial step in NASA's mission to take humans deeper into space, with a dedicated and passionate team ensuring the spacecraft's success. Technicians at NASA's Kennedy Space Center, working in the Vehicle Assembly Building, VAB, removed foam insulation and test sensors from Space Shuttle Discovery's external fuel tank, ET. This process was part of efforts to investigate cracks found on the tops of two 21-foot-long, U-shaped aluminum brackets located in the intertank area. These cracks had previously caused a delay in Discovery's launch. By removing the foam and sensors, NASA could perform additional X-ray scans of the intertank region to better understand the extent of the damage and confirm the effectiveness of repairs. These tests are crucial in ensuring the structural integrity of the tank, as well as preventing further issues in future launch attempts. The investigation was key to addressing the safety concerns that scuttled the previous launch, and the data gathered from these scans would help NASA decide on the next steps for Discovery's mission. Chandrayaan-2, India's second lunar exploration mission developed by ISRO, was launched on the 22nd of July 2019 from the Satish Dhawan Space Center using the LV-M3M1 rocket. The mission, following Chandrayaan-1, was designed to explore the Moon's surface, focusing on its composition, topography, and the presence of water. The spacecraft consisted of three components: a lunar orbiter, the Vikram lander, and the Pragyan rover, all developed domestically. Chandrayaan-2's primary scientific goal was to map the Moon's surface and study the abundance of lunar water, particularly at the South Pole. The mission also aimed to create 3D maps of the lunar surface and analyze the presence of hydroxyl and water ice. On the 20th of August 2019, Chandrayaan-2 successfully entered lunar orbit. However, during its attempt to land on the Moon on the 6th of September 2019, the Vikram lander crashed due to a software issue. Despite this setback, the orbiter continues its mission, sending valuable data back to Earth and furthering scientific research. The total mission cost was 9.78 billion rupees, approximately $141 million, making Chandrayaan-2 a remarkable achievement in low-cost space exploration. The orbiter continues to function, conducting studies on lunar mineralogy and the exosphere. A follow-up mission, Chandrayaan-3, was launched in 2023, successfully achieving a soft landing on the Moon, further advancing India's lunar exploration ambitions. The name, Chandrayaan, means mooncraft in Sanskrit, symbolizing India's commitment to space exploration. In a rare and detailed view, Space Shuttle Atlantis was captured in high definition as it was prepared for towback to its hangar after landing on May 26 following the STS-132 mission. Every shuttle landing involved a team of around 150 workers who assisted the crew and readied the shuttle for towing. A large diesel-driven tractor then transported Atlantis to Orbiter Processing Facility 1, where it would undergo post-flight servicing. Over its 33 missions, Atlantis carried a total of 207 crew members, some of whom flew to the Mir space station and the International Space Station, ISS.
down here? You need to wipe the seals though.
Not all launched and landed on Atlantis, as some were dropped off or picked up during its missions. Only 146 astronauts both launched and landed aboard the shuttle. Among the many remarkable individuals who flew with Atlantis, Jerry Ross holds the record for the most flights, completing 5 missions aboard the shuttle. Atlantis also played a role in historic firsts for several countries. Rodolfo Neri Vila, who flew on Atlantis in 1985, was the first Mexican in space. Similarly, ESA astronaut Dirk Frimout became the first Belgian in space on STS-45, while Swiss astronaut Claude Nicolier and Italian astronaut Franco Malerba achieved national milestones on STS-46. In May 2009, astronaut Mike Massimino, who flew on Atlantis during the STS-125 mission, became the first person to send a tweet from space. Additionally, astronaut Stephen Bowen made history as the first NASA astronaut to be launched on consecutive missions, flying with Atlantis in May 2010 and with Discovery in early 2011. Space Shuttle Atlantis, Orbiter Vehicle Designation, OV-104, is one of the most iconic spacecraft in NASA's Space Shuttle fleet. Built by Rockwell International in Southern California, Atlantis was delivered to NASA's Kennedy Space Center in April 1985, and it was the 4th operational space shuttle to be constructed.
Go ahead at 6. Verified. Verified. Yes, sir.
Atlantis played a significant role in NASA's human spaceflight program and, over the course of its career, became a symbol of American ingenuity and exploration.
Verified.
Early missions and Cold War operations.
Verified.
Atlantis made its maiden flight on October 3, 1985, with the mission STS-51J. This mission, which lasted just 4 days, was a classified operation for the U.S. Department of Defense, as Atlantis was equipped to support military and national security objectives during the final stages of the Cold War. Just 50 days after this inaugural mission, Atlantis embarked on its second flight, STS-61B, marking the shortest turnaround between shuttle missions for any orbiter at the time. This quick succession of flights demonstrated Atlantis's reliability and the intense demand for space shuttle missions during that period.
6 open talkbacks. And I can verify fuel cells, all 3 switches center with 6 gray talkbacks.
There, you got some water?
These early missions were not without risk. During STS-27 in December 1988, Atlantis sustained significant damage when a piece of insulation struck its heat-resistant tiles during launch. Over 700 tiles were damaged, including the complete loss of 1 tile, yet Atlantis managed to return safely to Earth. The severity of this damage went undetected due to the classified nature of the mission, which limited the quality of images sent to mission control. The crew's safe return was partly attributed to a steel antenna plate positioned beneath the missing tile, preventing a potentially catastrophic outcome. Interplanetary achievements. Atlantis made history by launching interplanetary probes that expanded our understanding of the solar system. In 1989, during the STS-30 mission, Atlantis became the first shuttle to deploy a planetary probe, Magellan, which was sent to map the surface of Venus. Later that same year, the Galileo spacecraft was launched from Atlantis on its journey to Jupiter, which contributed to groundbreaking discoveries about the gas giant and its moons. The Shuttle-Mir program and international cooperation. Atlantis was a critical player in international space collaboration, particularly during the Shuttle-Mir program, a partnership between NASA and Russia. Beginning with STS-71 in 1995, Atlantis made 7 consecutive flights to the Russian space station Mir, marking significant milestones in human spaceflight. The STS-71 mission was particularly notable, as it marked the first docking of a space shuttle with Mir and was also the 100th crewed spaceflight by the United States. Atlantis's ability to dock with Mir represented a significant step toward international cooperation in space exploration, laying the groundwork for future collaborations on the International Space Station, ISS. These missions also demonstrated Atlantis's capacity for long-duration flights and complex operations, as it ferried crew, supplies, and essential components to the Russian station. The docking of Atlantis and Mir created the largest spacecraft in orbit at the time, symbolizing a partnership between former Cold War adversaries.
We're doing good. Guess we're going to pull that inner cover off too, right, man? Yeah, after we switch out, we'll get everybody going. Okay. Take off.
Hello my friends and welcome back to the You Can Do TV channel. We're in the Brux plant, a leading supplier of seamless hot-rolled rings, flanges, and special forgings, renowned for its advanced production capabilities and exceptional expertise. The company operates a highly specialized manufacturing process in Ensheim, Central Europe, where it combines engineering excellence with innovative technologies to produce high-quality components tailored to customer specifications or industry standards. The production process here begins with a deep understanding of customer requirements, supported by engineering consulting and optimization suggestions. The company excels in various areas, including flange calculations, T-designs, swivel flange designs, and material selection. These services are backed by state-of-the-art technologies like 3D fee analysis, which ensures precision and reliability in the final products. The production process utilizes seamless hot rolling techniques to manufacture parts with impressive dimensions and tolerances. The company produces seamless hot-rolled components with diameters up to 6,400 millimeters, heights of up to 1,600 millimeters, and radial widths reaching 1,000 millimeters. The seamless rolling process allows for the production of parts with high structural integrity and minimal defects. Parts weighing up to 50 tons can be processed, ensuring that even large, heavy components meet stringent specifications. The company's production campus features large-scale forging capabilities, including an 8,000-ton press for manufacturing large parts with dimensions up to 4,500 millimeters by 4,500 millimeters by 10,000 millimeters and unit weights of up to 50 tons. The use of advanced forging techniques, such as simultaneous external and internal profiling, enhances the mechanical properties of the products, ensuring superior performance. In addition to large series production, the workshop is adept at producing individual and small series components with precise processing tolerances and surface finishes as fine as raw 0.3 micrometers. The company's ring rolling mill V, capable of rolling pieces up to 36 tons, exemplifies its dedication to delivering the highest precision and quality. Founded in 1974, Tironi Aluminum Shell Casting Foundry has built a reputable tradition in aluminum die gravity casting. This advanced process ensures the production of high-quality aluminum components, with a strong emphasis on precision and durability. Laboratory controls. To maintain exceptional standards, Tironi operates an in-house laboratory dedicated to quality and structural testing. This facility provides customers with reliable insights into the integrity of castings, ensuring consistency in the final products. Finishing. The finishing department eliminates imperfections through cutting, grinding, and deburring processes. These meticulous steps ensure smooth surfaces and remove excess burrs, preparing the castings for subsequent stages. Thermal treatments. Mechanical properties of sand-cast alloys are enhanced through specialized thermal treatments. Solution heat treating and precipitation heat treating significantly improve the strength and performance of aluminum castings. These methods align closely with techniques used for wrought products, ensuring optimal mechanical characteristics. Machining. The adaptability of aluminum enables extensive machining options tailored to customer specifications. Tironi's machining services are conducted with precision, transforming aluminum castings into components that meet exact design requirements. Mechanical Machining Department. Tironi's mechanical machining department excels in precision mechanics, prioritizing speed and flexibility to meet diverse customer needs. The company employs cutting-edge Industry 4.0 technologies, enabling real-time monitoring of each machining step. Advanced equipment includes multi-pallet CNC machining centers, lathes, and two three-dimensional measuring machines for accurate quality control. Specializing in turning and milling operations, the facility utilizes CNC machine tools with 2 to 5 axes. This capability ensures exceptional precision and efficiency, supporting the production of complex geometries and high-performance components. Through its comprehensive processes and modern equipment, Tironi Aluminum Shell Casting Foundry delivers superior quality castings and machine products, maintaining its legacy of excellence in aluminum manufacturing. Bersano Carlo is a leader in mold construction and hot forging processes, supported by state-of-the-art facilities that ensure exceptional quality and productivity. The company operates across 2 production sites, encompassing a total area of 20,000 square meters. These advanced facilities house specialized plants and infrastructure designed to optimize the manufacturing process, from mold design to part finishing. The construction of molds here is a process that begins with precise design and engineering. Every mold is crafted with high attention to detail, ensuring its reliability and durability in demanding industrial applications. After construction, the molds undergo rigorous quality checks and finishing processes, which guarantee their compatibility with subsequent forging operations. This seamless integration between design, production, and finishing underscores the company's commitment to innovation and excellence. Hot forging is another cornerstone of the workshop's expertise. With 11 dedicated production lines, the company delivers high-volume outputs while maintaining consistent quality. Hot steel forging involves heating metal billets to a temperature where they become malleable, then shaping them under immense pressure using the constructed molds. This process enhances the mechanical properties of the forged parts, making them robust and suitable for diverse applications. The CNC milling process for camshaft gear by UVA involves precise and controlled cutting of AC45 steel material. The process starts with a feed rate of 2,800 mm per minute, using a spindle speed of 18.00 rpm, U per minute, which allows the tool to efficiently remove material at a high rate. Cutting parameters such as the cutting speed and feed rates are carefully adjusted to optimize performance and tool life. For subsequent stages of machining, the process includes variations in spindle speeds and feed rates to achieve different cutting depths and qualities. At 8,000 rpm, the feed rate is reduced to 1,250 mm per minute to maintain precision. When cutting at higher speeds, such as 5,400 rpm, the feed rate increases to 1,600 mm per minute for optimal material removal. The final stages of milling employ cutting speeds up to 400 meters per minute at 8,000 rpm, with a feed rate of 2,000 millimeters per minute. These adjustments ensure the final shape of the camshaft gear is accurately produced, with smooth surfaces and tight tolerances. The use of high-precision CNC machines guarantees the necessary consistency, ensuring that the camshaft gears meet the required specifications for performance in engine applications. Fusin Rostogno specializes in high-quality manufacturing processes tailored to meet diverse customer requirements. The company offers both raw forged items and fully heat-treated components, ensuring precision and reliability across a range of applications. The production process begins with hot forging, where raw materials are shaped under high temperatures to achieve the desired geometry and strength. This is followed by hot ring rolling, a specialized technique for creating seamless rings with consistent dimensions and properties. Heat treatment further enhances the mechanical properties of the components, such as hardness and resistance to wear, making them suitable for demanding operational conditions. The final step involves precision machining, ensuring that each piece meets strict dimensional and surface finish standards. The product portfolio includes epicycloidal crowns, conical crowns, synchronizing rings, gears, rings for bearings, gears, and hubs, with dimensions ranging from 60 to 750 millimeters in diameter, a maximum height of 200 millimeters, and weights between 1 and 65 kilograms. These products are critical in industries such as automotive, agriculture, railways, excavators, rolling bearings, and transmissions, reflecting the company's commitment to versatile and robust solutions. The CNC deburring and chamfering machine is a high-tech solution designed for precision processing of gears, sprockets, pinions, shafts, and internal gears. It is equipped with 2 machining units, each featuring a deburring and a brushing tool. These tools chamfer both the top and bottom of the gear teeth, while also performing final cleaning to remove secondary burrs. The machine operates with advanced CNC control, utilizing 7 axes to ensure precise, repeatable, and fast positioning. This enables efficient handling of different parts, reducing setup times significantly. Thanks to its innovative CNC control system, the machine can save up to 50 operating cycles, further streamlining the process. The machine's simplicity and functionality are highlighted by its intuitive teach mode, where operators can input necessary data and program the operating cycle. The automatic loading and unloading configurations further enhance its efficiency, making it ideal for high-volume production while maintaining top-notch quality. This machine represents the latest in Italian engineering, offering both reliability and cutting-edge technology. The AGFM Forging Machine 8040 is a fully integrated precision radial forging system designed for hot forging applications, particularly for the production of long, fully hollow transmission shafts. It incorporates a variety of advanced features that enhance both efficiency and precision during the forging process. This machine employs the SKK-type radial forging machine, which is known for its versatility and ability to create complex part geometries with optimal material properties. The forging sequence begins with the blank loading conveyor, which transports the raw material to the robot handling system. The part is then placed into the induction heating system, where it is heated to the required temperature for the forging process. The system is equipped with a graphite spraying feature, ensuring optimal lubrication during the forging process and preventing material adhesion to the mandrel. The blank is initially forged over a stepped mandrel, which shapes the material into the desired form. This first side forging operation is crucial for defining the outer shape of the part. After the first side forging, the part is turned and reclamped to prepare it for the second side forging. This ensures that the material is uniformly forged to achieve the necessary dimensions and properties for the transmission shaft. The radial forging system allows for near-net shaping of the internal and external diameters, ID and OD, of the transmission shaft, reducing material waste and enhancing precision. Once the forging process is complete, the part is unloaded onto a conveyor for cooling. The offload cooling conveyor ensures the part cools evenly, preventing any distortion or defects in the final product. The flexibility of the AGFM Forging Machine 8040 is evident in its ability to handle different forging conditions, including cold, semi-hot, or hot forging, all on the same machine. This wide application range is achieved using a single tool set, making the machine highly adaptable to various production needs. The system's advantages are numerous. It enables new possibilities in part design, offering an ideal fiber contour for enhanced material properties. Material savings are achieved through near-net shaping, and the process eliminates the need for special surface treatments. The quick setup procedure on the single-station machine ensures minimal downtime and maximizes productivity. The Toyota GS300HCNC Horizontal Axis Gear Machining Center revolutionizes gear production with its innovative multitasking capabilities, offering industry-leading precision, speed, and reliability. It is the first horizontal machining center globally to incorporate gear skiving as a standard function, enabling efficient mass production of gear parts. The GS300H integrates multiple processes, including lathe operations, gear skiving, and traditional machining center tasks. This seamless combination reduces the need for separate machines, minimizing equipment usage and cutting tool costs. Its ability to handle continuous machining on the shop floor enhances productivity and flexibility. Key features: high precision, designed for ferrous, non-ferrous, and high-temperature alloys like titanium and stainless steel. Travel ranges: X-axis, 28.7, Y-axis, 25.6, and Z-axis, 33.5, with a B-axis rotating range of 270 degrees. Spindle performance: BBT number 50 spindle nose, 6,000 RPM speed, and 40 HP, 30 kilowatts, power. Large workpiece capacity: accommodates a maximum swing diameter of 31.5 and workpiece diameter of 8.66. Cutting efficiency: rapid feed rates up to 2,362 IPM and exceptional torque for demanding operations. Introduced at IMTS, the GS300H transforms gear cutting, making it ideal for automotive drivetrain components and beyond. By integrating advanced skiving and machining capabilities, this machine sets a new benchmark for precision manufacturing.